So in 6.4, we're talking about inverse functions. This is another really important step in expanding our library of functions and kind of what we know about a function. So let's start with what it means to have an inverse function. So an inverse function is a function, obviously, whose domain and range are interchanged from the original function. So here is my original function f. And right now it's for kind of the sake of keeping it simple, just a set of ordered pairs, right? We have 0, 6, 1, 4, 2, 2, 3, 0, and 4, negative 2. And I could actually plot these points if I wanted to. So maybe I'll do that first. So you have 0, 6, 1, 2, 3, 4, 5, 6. Oops, whoa. 6, 1, 4, 2, 2, 3, 0, and 4, negative 2. So I have my 4 points, my 5 points here that make up my function f. I don't know why that keeps happening. And then we said that the definition of an inverse function is to take our domain and range, right, our x and y. So our domain and range. And interchange them, change their positions. So instead of x being 0, 1, 2, 3, 4, that's going to become y. So y will be 0, 1, 2, 3, 4. And then my x will become what y used to be, 6, 4, 2, 0, negative 2. And I can also plot these. So I have 6, 0, 1, 2, 3, 4, 5, 6. 4, 1, 2, 2, 0, 3, and negative 2, 4. So we've got our points plotted, excuse me. And I want to know kind of what do we observe here about a function and what I'm defining to be its inverse, right? So I have a function, any old function, and then that we said that g of x right now we've defined so that it's an inverse. Well, we've maybe observed two things. All our x's become y's, and vice versa, right? Y becomes x. And we might also notice some symmetry here. Actually, it might be clear if I were to connect these dots with a line. So if I were to, yeah. And then if I do this with my blue points, get it to go right on the, nope, hold on. Try this again here. All right, hold on. One more try. There we go. All right, if I would connect these points like I've been trying to do, you notice that they meet at a point here in the middle. That's not necessarily going to happen every time, but more importantly, there's some symmetry here. There's a mirroring over the line y equals x. So if I draw that in as a dotted line here, you can actually see that there's some mirroring going on here, right? If I consider this to be my line to be a mirror, and I take a point here, it's getting reflected over this line to become this point over here, right? 1, 4 becomes 4, 1. 3, 0, 0, 3 becomes 3, 0. 0, 6 becomes 6, 0. There's a sort of mirroring going on, a symmetry here. So there's a symmetry over the line y equals x. That's what this is right here, the line y equals x. So I'm going to put those lines back in if it works nicely, just so we have them as a reference. And I think it's easier to see that sort of symmetry if you actually see the lines drawn in. Okay, so this is kind of what it means to have a function and its inverse, right? We have this interchanging of x's and y's. But we can actually define this further, and we can define this a little more concretely mathematically. If I say this, two functions f and g are inverses if and only if, which is just a logic term saying I can read this sentence that I'm about to write both ways, forwards and backwards. So f and g are inverses if and only if f of g of x equals x and g of f of x equals x. And you remember in the last video that this is just a way of writing this, right? F of g of x and g of f of x. And I get x. If this is true, so if g is an inverse, or the inverse, I suppose, of f, g is notated as f inverse of x. So this is a little bit new. And it's really important to note here that this notation here does not mean 1 over f of x. So here, it does not mean a reciprocal. This is super important. So right here, this notation does not imply a reciprocal. It's just to say it's the inverse. It's the function that undoes another function. And we're already used to this, right? Some examples of inverses. If I have a function that is x squared, then its inverse function is the thing that undoes x squared, right? It's square root of x. If I had like x plus 1, well, what's the thing that's going to undo adding 1? It's going to be subtracting 1, right? So we're kind of used to this a little bit already, just maybe not in a formal context. So the first thing we're going to do is use this definition that we've just come up with. Prove that these two functions, 3x minus 5 and f inverse of x equals 1/3 x plus 5/3, are inverses. So how do we do that? Well, we need to check two things. Use a lighter color here. I need to check that f of g of x is x and g of f of x is x. So no matter which way I compose them, they cancel out. So let's check that. If I check f of g of x, well, this notation isn't the most helpful, except I think it's a little easier to write. So let's use our more helpful notation to start. So f of g of x. Well, actually, I shouldn't be using g at all here, should I? I should be using this f inverse notation because that's the name of my function. There we go. So f of f inverse. So I'm going to plug f inverse here into my function. So this is going to be f of 1/3 x plus 5/3, which is to say, take 3x minus 5, and where I have an x, I'm going to replace it with my function. So let's simplify. We'll distribute the 3, combine like terms, and I get x. So this works out that way. That's good. Let's check it the other way. If I check f inverse of f, and again, I think it's easier to write out this notation instead because I think it makes it a little more clear. So instead of plugging in f inverse to f, I'm going to do the opposite and take my f and plug it into f inverse. So this is to say we're going to take 1/3, actually before I do that, say take f inverse of 3x minus 5. So I'm going to get 1/3 x, whoops, we get 1/3 3x minus 5 plus 5/3. So let's simplify. Let's distribute. Let's see, I get x minus 5/3 plus 5/3, and I cancel out the like terms. I get x. It all checks out, right? So I've been able to compose it both ways. Everything cancels out, and we're good to go. Well, a lot of times it's going to be more helpful to actually find the inverse, not just check that something is an inverse. And we have a lot of steps. We have a few steps we can follow to do this. So I think it's most helpful here to actually walk through an example as I'm doing this. So I'm going to kind of do this side by side. And my first step is to replace f of x with y. So my first step here is to call this y instead of f of x, just because it's going to make my notation and my work a lot easier. Second step is to switch x and y. This is an important first step. So I'm going to, where I have a y, I have an x. Where I have an x, I have a y. So far, these two steps are pretty straightforward, right? Not a lot of work, just a lot of notation, a lot of just preparing to do this problem. So step 3 is to solve for y. So this is where I actually have a lot of my work to do. So I'm going to subtract 3, and I'm going to divide by 2. Or if I wanted to, I could have written it as multiplying by 1/2, so this would be acceptable also. If you chose to distribute that, that would be acceptable also. Any of these is fine. They all mean the same thing. Once I'm done with that, I'm going to replace y with, well, let's think about this. I found the inverse of the function, so instead of calling it f of x, I'm going to call it f inverse of x. So f inverse of x equals, equals x minus 3 over 2. There's my function. There's my inverse. How do I know it's an inverse? Well, I won't always ask you to verify, but it's good to know how. So I'll just say if asked. Like, just be ready to show that it works out. So we're going to do that. Let's check f of f inverse first. So if I plug in f inverse into f, so if I say 2 times f inverse plus 3, well, my 2's are going to cancel. So I'm left with x minus 3 plus 3, which is just x. So that works. And if I do this the other way, then that would give me 2x plus 3 minus 3 over 2. Well, let's see here. My 3's are going to cancel out. Whoops. So that's going to give me 2x over 2, which is just x, so I'm good. So yeah, this actually is my inverse. So the inverse function is x minus 3 over 2. Let's try one more. So find f inverse if f of x is given here. Verify your answer. Okay, so let's follow the same steps. I want to replace f of x with y. So that's just to say y equals 2x squared minus 4. I want to switch x and y. So I'll have x equals 2y squared minus 4. And then I want to solve. I'm going to divide by 2 or multiply by 1/2, whatever you feel like. I'm going to take the square root. And so normally when we do this, it would be plus or minus. But something that we're going to do with inverse functions with even powers is actually we can ignore kind of this plus or minus and only deal with the positive part. And that's just so our inverse is actually a function, and I'm going to talk about that in a minute. And then, of course, my last step is to replace y with f inverse. So f inverse of x is, we'll just consider the positive square root or the so-called principal square root, and we get x plus 4 over 2, the square root of x plus 4 over 2. And then I'm asked to verify, so let's do that too. First thing I want to verify is f of f inverse. And that's the way to say f of f inverse. I like this notation better to when I'm actually working with it. So this would be 2 times the square root of x plus 4 over 2 squared minus 4. And this one looks a little bit tricky, but it's okay. I notice that my square root and my square will cancel out, which will be helpful. So it leaves me with 2 times, x plus 4 over 2 minus 4. So my 2 and my 1/2 will cancel out. That leaves me with x plus 4 minus 4, which equals x, which is nice. And then I can check this the other way too, right? I need to check, I have to. F inverse of f of x. Try to save a little bit of room so I have room for my definition below. So I'm going to actually plug in my, whoa, it keeps happening. 2x squared minus 4 plus 4 over 2. That looks gross, but it's not that bad, I promise. The plus 4 minus 4 cancels out, and that leaves me with 2x squared over 2. The 2's cancel out. I have square root of x squared, which is just x, so I'm good. And I've found and verified my inverse function. I mentioned in passing really quickly just now that sometimes we kind of ignore this plus or minus and deal with just the positive version of a square root, and that's to make sure that my resulting function is really a function. So this is actually related to something called the horizontal line test. I'll keep the same color, which is to say that I'll say that f inverse is also a function. Here's a if and only if again. A horizontal line passing through f, not f inverse, just f, never intersects the graph of f more than once. If you remember like the vertical line test, right, where we take a vertical line through a graph to see if the graph is a function, it's the same thing, just horizontal. Here's what I mean. If I were to take a horizontal line, and I really hope I can pick this up and move it, that's not horizontal. It'd be really helpful if I could just pick up a horizontal line and move it. Let's see if this works. Yeah, all right. If I take this horizontal line here, and I were to pass it through, however bumpy, my function, it never intersects the graph in more than one place, right? Whatever I do, no matter where I draw this horizontal line, it only intersects the graph in more than one place. So this tells me that f inverse of this function will also be a function. However, if I draw another horizontal line here, if I try this with something like g of x, and maybe you can already see it, no matter where I draw this horizontal line, I will always intersect the graph in multiple places, and in this case it's 2 places. So if I were to draw in this horizontal line here, you notice that I intersect the graph twice, 1, 2. And this tells me that the inverse of this function will not also be a function. Right, if I were to draw this in, if I were to actually draw in what this inverse function looks like, and I'm kind of eyeballing it here, but it would look roughly something, I need a different color. It would look something roughly like this. I'm going to put it in quotes because it's not really quite a function yet. It would look something like this. That's not a function, fails the vertical line test. So what is a function? it's a function if I consider just this top piece. Right, this part kind of represents this piece over here, but it doesn't really make it a function. I want to make sure my inverse is always a function, and that's why, like I said before, that we kind of ignore that, that plus or minus and just stick with the positive part. It makes my life a lot easier. So I believe this is my last example, right? Yeah. So I want to find the inverse of this function and determine if the inverse itself is also a function. So let's try it. Same steps as always, right? Interchange or switch f of x out for y. Switch their places. And solve. So I'm going to subtract 1. Divide by 2. Take a square root. And then replace y with f inverse of x. I'm not going to verify it right now for the sake of time, but if you want to pause this video and practice it, you're more than welcome to. And also for the sake of time, I've graphed the two functions, and this is something that you can do on your calculator. You can, if I were to do this on my calculator, I would input these three functions. So I would input 2x cubed plus 1, my original function, and I would input my inverse. If you want, you can enter in y equals x, but sometimes you can see this intersection fine from just y1 and y2. You can see that there is a symmetry here, right? Y equals x acts as a sort of mirror, kind of connecting, say, these 2 points together, for example. There's kind of a reflection. So yeah, I would say A, that f inverse is in fact the inverse, and I would also say that it's a function, right? If I take a horizontal line, for example, maybe here, you see that it only ever intersects in one place. So f inverse is a function. And actually, you can also check this by just seeing that f inverse, in this case, passes the vertical line test. So you're kind of good there too. Either method is fine.